Hello everyone, my name is Stephen Maciong and I will be your presenter today. If you can please answer a polling question as we wait for everyone to log in, I would appreciate it. Thank you. After about 2.5 minutes of polling, 84% participation, the results are 50% are using a mixture of both LiDAR and photogrammetry, 24% are using exclusively LiDAR, 12% photogrammetry, and 9% none of the above. Those are the results. Okay. Good afternoon, everyone. Welcome to RIEGL USA's RIEGL UAV mounted LiDAR camera options and data colorization RiPROCESS webinar. To briefly introduce myself for those of you who are new to my webinars, my name is Stephen Maciong and I'm a technical sales and integrations representative for the unmanned LiDAR segment at RIEGL USA. I've worked in this position for roughly 1.5 years now, and before my time in sales, I worked in our support department, gaining valuable knowledge on RIEGL's hardware and software. Before we start the presentation, do note at the bottom of the screen the question box. Please feel free to add your questions during the session. I will do my best to answer them at the end of the presentation. Now, before we get into camera options that RIEGL offers and data colorization workflow, let's take a quick look at the unmanned LiDAR sensors that these camera solutions were designed for. Taking a look at the top row of LiDAR sensors, we see RIEGL's BUX series sensors in the BUX 240, the BUX 1LR, and the BUX 1 UAV. These sensors were each designed with their own strengths. The BUX 240 is optimized for high-resolution corridor scanning, producing up to 1.8 million laser pulses per second, focused in a 75-degree field of view. While the BUX 1 UAV has a 330-degree field of view capabilities and a 5mm relative precision rating. Then there's the BUX 1LR, which was designed for larger project sites where data needs to be captured at faster ground speeds, such as when flown from a helicopter. The bottom row of LiDAR scanners is RIEGL's powerful lightweight Mini BUX series LiDAR sensors. The latest addition to the Mini BUX series is the Mini BUX 2 UAV, which maintains the same weight and form factor as the popular Mini BUX 1 UAV, with twice the point cloud density output at only a few percentage points of the bottom line cost more than the Mini BUX 1 UAV. All of the Mini BUX series sensors also have multi-target capability and a relative accuracy rating of 1.5 centimeters. The Mini BUX 1DL rounds off the Mini BUX series as a cost-effective LiDAR sensor with a restricted 46-degree field of view, which makes this sensor optimized for corridor mapping. To meet customers' needs for flexibility and performance and payload weight, RIEGL has developed several RGB camera solutions for its LiDAR systems. We currently offer RGB camera options in the Sony Alpha 7R III, Sony Alpha 7R, and Sony Alpha 6000. The megapixel resolution output of each Sony camera RIEGL offers is as follows. Sony Alpha 6000 has an expected 24.3 megapixel resolution. The Sony Alpha 7R has a 36.4 megapixel expected resolution, and the Sony Alpha 7R III has an expected 42.4 megapixel resolution. In addition to the Sony cameras that we offer, RIEGL also offers Phase 1's IXM50 and IXM100 cameras. As with the Sony cameras, the Phase 1 IXM50 and IXM100 cameras are excellent aerial cameras, with the IXM100 camera producing 100 megapixels resolution with a pixel size of 3.76 micrometers, very small. And the IXM50 produces 2 expected 50 megapixel resolution, as the name might suggest in the IX50, with a pixel size of 5.3 micrometers. If you look at the images on the bottom row, you will see an image of a Phase 1 camera integrated onto a BUX 240 LiDAR system that is being flown on RIEGL's UAS platform, the RiCopter. The image on the right is a better view of the mounting structure for the camera. The weight of either Phase 1 camera offered with the RS28mm lens is approximately 1.7 kilograms or 3.7 pounds. In addition to the RGB camera options RIEGL also offers thermal and multispectral camera options, but we will get into more detail on those camera options later in the presentation. Now let's take a look at the different mounting orientations that RIEGL offers for its cameras. For the Sony Alpha 6000, RIEGL offers a dual oblique and oblique narrow camera mounting options for its Minivux series sensors, and only a wide oblique setup for its Vux series sensors. The option to choose between a wide and narrow dual camera setup was designed to fit UAV platforms with narrower payload space, for instance. For instance, RIEGL has designed an integration kit for DJI's M600 Pro, and the narrow dual camera setup is necessary to fit both cameras within the payload area in between the landing legs. Next, we'll look at a traditional LiDAR camera orientation and how this orientation is offered for all camera options that RIEGL offers and can be mounted in the fashion on all RIEGL unmanned LiDAR sensors. Lastly, RIEGL offers a thermal camera option in the Tau-2 in a LiDAR orientation. In the image on the bottom row of this slide, we see the Tau-2 mounted on the front of the Vux 1 UAV LiDAR sensor. Now let's take a look at lens options for the Sony cameras that RIEGL offers. For the Sony Alpha 6000, a 16mm pancake lens is offered with or without IR filter. For the Sony Alpha 7R and the Alpha 7R3, lenses manufactured by Zeiss and Voigtlander are available with varying lens dimensions for a wider or narrower image result. As a friendly note and reminder, it is best to keep in your mind your typical applications of LiDAR and imagery when selecting your lens type. If you would like to learn more information about the weight or performance of RIEGL's camera lenses, please contact one of RIEGL USA's sales representatives such as myself, and we can assist you in gathering your sought after knowledge. All right, now let's take a look at some weight breakdowns for different RIEGL LiDAR system configurations with the Sony RGB cameras. As can be viewed in this slide, RIEGL's LiDAR system weights with additional cameras range in weight from 2.27 kilograms or 5 pounds to 6.21 kilograms or 13.69 pounds. Some weight breakdowns for RIEGL's Sony camera options are as follows. Sony's Alpha 6000 weighs approximately 0.34 kilograms or 0.76 pounds. Sony Alpha 7R weighs 0.47 kilograms or 1.04 pounds. And the Sony Alpha 7R3 weighs 0.65 kilograms or 1.4 pounds. As with all UAV missions, flight endurance of the airframe is an ever-present consideration. And the lightweight options that RIEGL offers will help in this regard, allowing operators to fly longer and collect larger swaths of land on a single battery charge, which will enable you to collect your project site in a more efficient manner. RIEGL has recently just finished developing a partnership with Aggroing, which is a multispectral camera solutions company based in Israel. A multispectral camera solution with multispectral camera solutions utilizing the Sony Alpha 6000 and the Sony Alpha 7R3 cameras. One of the products that Aggroing has developed are multispectral camera lenses that adapt to Sony RGB cameras that RIEGL currently offers, with some modifications for integrations of these lenses made by RIEGL. This is an exciting release as multispectral cameras have a value in the agricultural industry, as well as in identifying vegetation species and mineral identification based off of electromagnetic absorption or reflective properties of the matter being scanned. Adding these cameras to your system expands the amount of deliverable information you can collect in a single scan and increase the overall value of your data set based on this fact. Now let's see an example of multiple camera options brought together in one integration. The image on the right has 4 sensors in total, and RIEGL was able to design an integration solution that would fit all of these sensors onto the Minivux SIS LiDAR sensor and be able to mount this all onto a DJI M600 Pro. The four sensors shown in this picture are as follows. The Minivux 1 UAV LiDAR system, that's the key right there. Additionally, a Sony Alpha 6000 RGB camera, and Then we have our multispectral camera here, which is the Firefly 185 multispectral camera. And lastly, the smallest and most lightweight sensor on there is the FLIR Tau 2. To provide some additional information on the FLIR camera that RIEGL offers, the specific camera that is used is the FLIR Tau 2 640 13mm camera. It's lightweight at 0.72 grams or 0.16 pounds and has a 0.33 megapixel resolution. All of these sensors combined make for an impressive solution for applications that require this depth of information. And now that we have gone over the different hardware, let's move on to another poll question. Let's take about a minute to answer this. I'll relay the results to you and we'll continue on. All right, this is very encouraging. We're 30 seconds in and already 75% participation. Right now, it's about a three-way tie for first place with RGB, RGB and thermal, and multispectral. 33% of you said that you were interested in RGB cameras. Only 2% for thermal. Okay, and let's see, what else do we have here? 33% for RGB and thermal combination, and 31% of you are interested in a multispectral camera solution. Okay, moving on. Now let's transition to the second half of this presentation and walk through the workflow for colorizing your LiDAR point cloud in RIEGL's post-processing software, RiPROCESS. There are four main steps that you will want to follow for colorizing your data set, and they are as follows. You want to run the data wizard. You want to run the camera mounting wizard. You'll want to run the color scan wizard. And finally, once all of those wizards are complete, you'll want to export your colorized LAS file. Let's take a look at the workflow and the purpose of each step now. The first step to perform in the camera data wizard, and this can be found, this wizard can be found under the Tools tab. The purpose of the camera data wizard is to link your images with your point cloud via their timestamps. So as we can see here in step one, we are now importing the images captured from the RGB camera during our mission and uploading them into the camera data wizard in RiPROCESS. Our next step is to select all the records, which are files that contain point cloud information, and upload them into the camera wizard as well. Once the images and records have been uploaded, now is the time to locate the timestamps associated with the images and upload that file as well. The location of this timestamp file is within the EIF folder that is located in the CAM raw folder, which can be located within the main project file structure that you download from your LiDAR system after your mission. So you collect your data, you download your data onto your processing computer. You're going to get a file structure of multiple files, whether it be camera raw file, raw LiDAR data, etc. And you're going to locate the CAM raw folder, and within that folder is the EIF folder. All right, and while we still have steps to go, this is the type of colorization that we are working towards. Next, the camera mounting wizard. The camera mounting defines the position and orientation of the camera with respect to the IMU coordinate system and is stored as a 4x4 matrix in the camera device object in the project. The camera mounting matrix can be calculated by defining corresponding points in the images in a 2D view and in the point cloud in a 3D view. And I'll go a little more into that here in a second. The first step is to select the camera that you'll be performing the camera mounting wizard on. In this case, we only have one camera, so we just select the one camera available. The next step is to select one record and the images associated with that record based off of the timestamps, and find planar objects such as road signs and billboards to link the imagery with the objects in the LiDAR point cloud. So as you can see here, we have a side-by-side view with the left side, the point cloud. Maybe you can't tell immediately, but that's what we're looking at here in a reflectance scaled view, grayscale. That's our point cloud. On our right side, this is our imagery. So what we're going to do is we're going to search throughout the project site for these planar objects, and then we are going to be relating them to each other here. Okay. The next step is to select one record and the images associated with that record based off the timestamps. Okay, we've been through that. You'll want to find at least a minimum of 3 objects to relate, and then run the camera data wizard to generate this 4x4 matrix that I had mentioned earlier. Lastly, after the camera mounting wizard has been calculated, go to your camera under the camera devices section in the project tab and select it. You can see this camera device right here. I don't know if you can see my mouse, but that's it. Okay, after selecting the camera, click on the mounting tab and right-click the matrix and export that matrix and save it. Save it for later. You can use this matrix for future projects to help save time in processing, given that you haven't removed the camera from its mount. So basically, this matrix that we've created after doing the camera mounting wizard is good for future projects, as ideally we would like you not to remove the camera from the mount. You know, extenuating circumstances and everything, but this will help you save time. Okay, another look at the finished product. Left is a reflectance view of the point cloud set to grayscale, and the right image is that same point cloud within the same project site, colorized in RiPROCESS. The last step that we have before export is the color scan wizard. And the purpose of the color scan wizard is to colorize the point cloud. Pretty straightforward, it's in the name. Simply select the records and the associated image files, then run the wizard. So as you can see here, we've selected all of the records in the left window, and we're getting ready to associate them to all of the images that are shown in the right window. And this is done simply by clicking this arrow, selecting all of your images here, clicking the arrow, and associating them to all, or the records on the left and associating them all to the imagery on the right. You press OK, that's it. The wizard runs, and all you have to do is wait for it to finish processing. All right, and here is the colorized point cloud now. And you can see the vantage point that we have from this view, which a mobile or terrestrial LiDAR sensor would not be able to capture. Lastly, we export our colorized point cloud by right-clicking Records in the Project tab and clicking Export Laser Data. This will bring up a menu option that will allow you to export into different file formats, such as the popular LAS or the RIEGL database. A quick note on the advantages of exporting in RIEGL's database format is it allows users to import their data directly into RIEGL's terrestrial LiDAR software, RiScan Pro, and data fuse both data sets, one terrestrial, one unmanned LiDAR sensors in this case, and we can data fuse those both together in RiScan Pro, and then you can export that into something like Esri, for instance. Another feature of note is that you can select different color channels if you have multiple camera types for your project. So let's say that you're flying with a multispectral camera and an RGB camera. You will export one LAS file or one RIEGL database file with the one color channel for RGB. And then you will have the option to export another file with just the multispectral for that file. So you have some flexibility there and ease of use. Okay, and then lastly, let's talk about exporting some of the imagery. If the camera data is co-captured, you have the ability to export your georeference imagery as well in either JPEG or GeoTIFF format. Additional information can be applied as well, such as ensuring the image is undistorted and outputting the image list in a format that is supported by your third-party analytics software. Thank you so much for joining me today. That's all the time I have today. If you have any additional questions, please feel free to contact myself or my colleague, Mike Mullen, directly. But before I close out, I want to see if there were any questions that were posed and try to see if I can get these. Okay, somebody is asking if we have a list of compatible UAV platforms. What I can tell you for certain is that we are compatible with the DJI M600 platform and the RIEGL Rycopter. Beyond that, we can have a more in-depth conversation about compatibility and other companies on a during a phone call or an email exchange, but right now I would point you in those two directions with the RiCopter, and if not the RiCopter, then the DJI M600. So reading through some of these questions, they're a little beyond the scope of what I'm prepared to answer during this forum, but I will, as I stated before, I will be reaching out to you and addressing these questions so that you can get the answers that you need. So I just want to thank everybody for listening in on this presentation, and I appreciate your time, and I hope to hear from some, if not all of you, very soon. All right, take care, everybody. Goodbye.